Okay, so hello everyone. Thank you all for coming to this SSC day. On the program for this afternoon, we have 3 talks by 3 internationally renowned researchers. So first, Dr. Andreia Cathelin from ST Microelectronics Kroll. She will bring us to the land of IoT, its application fields and integration challenges, and how the FDSOI technology features permit to tend toward the best-in-class energy efficiency and lifetime for IoT products. Then we will have Professor Philippe Tavernier from KU Leuven in Belgium. He will discuss well-known trade-off between speed, accuracy, and power consumption of Nyquist ADCs. And he will introduce a framework capturing the most significant effects and trade-offs on the building block level that will impact the ADC, and as well as the effect of scaling. And using this framework, he will compare the most popular ADC architectures. At 4 p.m., we will have a 15-minute coffee break, so we can relax and discuss about the first 2 talks. And finally, we will have Professor Danilo Manstretta from University of Pavia in Italy. So he will introduce us to the world of transimpedance amplifiers with design examples of closed loop and open loop topologies for transimpedance amplifiers for IoT, 5G, and optical receivers. So after this quick introduction of the afternoon, we are now beginning with the SSC day, starting with Dr. Andreia Cathelin. So Dr. Andreia Cathelin started electrical engineering studies at the Polytechnic Institute of Bucharest, Romania, and graduated with Master of Science degree from ISEN Lille, France in 1994. In 1998 and 2013, respectively, she received PhD and the French highest academic degree from the University of Lille, France. Since 1998, she has been with ST Microelectronics Kroll, France, now Technology Research and Development Fellow. Our focus areas are in the design of RF, millimeter wave, terahertz, and ultra-low power circuits and systems. She's very active in the IEEE community since more than 15 years, notably with Solid-State Circuit Society and its ADCOM. She is as well a founding member of the IEEE SSCS Women in Circuits group. She has authored or co-authored more than 150 technical papers and 14 books chapters, and she has earned many awards for it. She's also has co-edited the Springer book, The Fourth Terminal, Benefits of Body Biasing Techniques for FDSOI Circuits and Systems, and has filed more than 25 patents. And very recently, Andreia has been awarded an honorary doctorate from the University of Lund, Sweden, promotion of 2020. So, Andreia, thank you very much for coming to this SSC day. And now the floor is yours for your presentation.
Thank you very much, Maxandre, and thank you for your kind introduction. Thank you for having me today. There is something I have forgotten to send you out. Mm-hmm. This is that I have been the TPC chair of ESERC 2021, and at the end of this conference, we have the conference has made some benefits that were sent out to your student branch in order to fund such activities.
Thank you very much.
So thank you very much. So thank you. Can you hear me correctly?
Yes, we can hear you very clearly.
Okay, thank you very much. So today, for a bit less than 1 hour, we will be discussing about the FDSOI technology as a game changer in the IoT arena. I have also a subtitle for this presentation which says our designs change the world, and this is very important for you young people who are about to start your career in electrical engineering, to understand how you can act in order to bring in more, let's say, wealth and well-being on our planet. And I will give you some examples in order to help you identify yourselves. Okay, so let's. Okay, so this is the agenda of my talk today. So first of all, I will fly you through an example of IoT strategy inside a big company. And I will take an example of a company that I know well, which is the company in which I work, ST Microelectronics. Then we will discuss some details about the FDSOI CMOS technology, which is by construction energy aware, and you will see it's very well fitted for the IoT ecosystem. Further on, some system and circuit detail on a IoT solution using the 28 nanometer FDSOI CMOS technology, and it is related to a project called the Human Intranet. And then finally, I will conclude and bring you out some takeoffs. So first of all, so let's discuss about the example of an IoT strategy, so at ST Microelectronics. So our company is very strongly linked to Internet of Things, and we have made of it a strategic focus for our for a big part of our activities. So we are placing ourselves onto 4 pillars related to the IoT. So the first one, so you starting, let's say, small. We are talking about smart things. So smart things that are on you in your home, or I don't know, very close to you. Then you have the smart home per se as the building, as a premise. Then you have the smart cities, so that receive also the smart homes. And then you have also the industrial field, which is called the smart industry. So these are really very important 4 pillars of the IoT ecosystem. So now if we look, so IoT supposes a lot of connected devices that can allow things to talk one to each other, or things to transmit information one to each other. So they have to be wirelessly connected devices. So here I have let's say maybe not exhaustive list of different kind of applications that make usage of the connected devices. So I will not maybe read all of them, but let's just make some small focuses. So for example, inside a smart city, so all the, this is a very big actuality today in France. So we have the lighting system. So how can we consume exactly what we need as energy inside of a city? So we can have these connected devices now to control this. Of course, then traffic sensors, parking meters. When you enter a very big parking with a lot of cars and you want to know which place is taken or not. Then we have also a lot of connected devices for all the assets and people tracking, parcels, shipping, fleet management. Then you can have also environment monitoring that can be inside your house or outside, like air quality, fire detection, and so on. Again, home automation, lighting, smoke detection and security system, also inside an industrial premises, and also for sure inside a production halls, so industrial environment. So you have a lot of connected devices that permit also process and equipment monitoring, and so on and so on. So for mobile health solutions, and also for wearable devices. So you really have a multitude of such connected devices. So this is one end of the IoT ecosystem. Let's see how is this happening further on. So at one edge, so we have what we call the nodes. So the nodes can be what we have shown, like, I don't know, a watch or connected watch or whatever, they are either simple things or what we call smart things. A simple thing is what we call a connected object that captures some data and transmits it wirelessly directly. A smart thing is an object that captures some data, processes it a bit, and then transmits it. So where is this data transmitted? So this data can be transmitted in two different ways. So it's either concentrated inside gateways, which can be like, for example, the internet boxes at your home. And then this gateway is transmitting it to what we call the cloud, which is a network infrastructure and servers. Or you might have some smart things, some smart nodes that transmit their data directly either to the network infrastructure or directly to the servers. So this is the structure of an IoT full network, okay, with the three different segments: nodes, gateways, and cloud. And there are a multitude of objects and of integrated circuits and systems that serve this. And what I am showing here, to come back to ST, so we are producing solutions that are able to serve the three segments inside the nodes, the gateways, and the clouds, with all these pictograms that you can easily understand what they mean, and we will discuss also later on. Now, there is also a very interesting trend in terms of the data that we transmit, and also related to the energy efficiency of an IoT network. So the first solutions that we had on the market, so you had these IoT nodes that were transmitting this data, maybe with a bit of processing, directly, maybe through a gateway, but directly to the cloud as it was. And this means that per se, this kind of network needed a high bandwidth and to transmit all this data like that, and also so this implied high power, and but still it had to stay at a certain amount of power consumption. So at the end of the day, it was limiting the services that we could provide, because we couldn't transmit such a very large quantity of data and to treat it. So then the trend, what came after at second and afterwards generations of IoT, was to have nodes with a lot of more or less sophisticated analytics. So this means data collection and data processing inside the node, but still staying very low power. And then what we transmit is now not anymore raw data, but it is a metadata. So it is data compressed or with some modulation on it and so on. So this enabled us to consume less power overall for the overall solution, and to support more and more IoT nodes. And also, if this data is processed immediately on the node where it is created, then by construction we can enable it with enhanced privacy and security when we transmit it over the air. And also at the higher level, at the cloud level, we can provide more value and more services on this metadata. So as of today, a very large majority of new IoT solutions operate on this system. Okay, so now if we look of what are exactly these IoT nodes or these IoT collection points. So they really come in our day-to-day life in many form factors. So you can have the small objects that you recognize, that you all wear a connected watch or a connected whatever, or I don't know, something on you connected. You can have also all the other kind of connectivity objects. I mean, a phone, a mobile phone, can be also seen as an IoT node or even more nodes. You can have also some gaming stuff. You can have some connected objects in your home. Then you can have all these connected things inside your houses, more or less big. Here, for example, you can even recognize the Linky power meter in your house, and then all these other solutions in industrial field, and also you can also even talk of car auto radio. So the IoT devices really, and this is really a very big revolution in the field of communication objects. They are the same category, but they really come in many form factors. And all so they come in many more in different form factors. Their needs in terms of system and implementation are the same. So here you find the 4 big pillars for IoT: smart things, home, city, and industry. And here we can group their needs in terms of system and implementation can be grouped in 5 different categories. So you can have, first of all, so all of them, they need processing and security. And it can be declined from ultra low power to high performance. And also the degree of security they need can be scalable or declined upon the application. So generally they all connect to different other kind of physics. So they are all enabled with sensors and actuators. And then you have a very wide range of such sensors and actuators. They all need to talk wirelessly to the network. So they all have connectivity. And this can be either from a very short range, ultra low power, or for longer range up to 10. It's not even 10 kilometers, it can be even more than that. Okay, they all need signal conditioning and protection and circuitry for power and energy management. Okay, so this is very, let's say, like the concept of IoT, so it's very interesting. So now for the next few slides, I would like to give you some examples of architectures of these generic architectures of IoTs, and also some examples regarding the sensors, the microcontrollers, and the types of security that we can apply on them. So here, this is a generic architecture of an IoT machine-to-machine let's say node. So it is enabled with connectivity, with sensors, processing, and power management. So you can follow the color codes here. So for the connectivity, for example, you have kind of a transmit-receive radio with a classical, let's say, radio architecture that you must have learned in school. You have the signal processing, so the data conversion here at the edge, and the digital signal processing. You have also connection to the different sensors, and also generally these are battery operated objects and connected to the power management unit that is fabricating the different power supplies needed on chip. So here, depending on the type of IoT object that we will do, we will use, so for let's say financial aspects, so for cost efficiency, so all this has to be integrated onto one chip, what we call a system on chip. And the silicon node, so the CMOS technology that we will be using is a matter of the IoT segment. So do we want a cheap and disposable product, or do you want a high-end product? How long is its lifetime, and so on and so forth. So now in terms of connectivity, so also, as I said, the connectivity can be very local, very low range, up to very long range. So sorry, there is an error here. And also the data rate that we need to transmit can be very low data rate up to much higher data rates. So we have a multitude of standards existing on the market that are serving all these types of connectivities, and as all is matter of power consumption, you cannot use a very high-end connectivity standard that is consuming a lot if you want to transmit very few data rate on a very local range. So this means that upon the need that has your IoT network, you will choose the type of connectivity which is the most closely matched to your need in terms of data rate and connectivity range. And this gives you different scenario of usage. So here, this is the example of the connectivity scenario inside a domestic. So this is the smart home, connected home, where you can see a lot of connected objects inside your house, and you can see that they will be using different types of standards in order to communicate, and for each of them there will be the most, let's say that they will have the best energy performance matched to the need that you have. And you see, so all these kind of connections inside your house, and also the connectivity to the fixed wired network that can exist from on the houses inside the grid, like the internet grid in a city, or even the power grid, and also interconnection with the cellular operator servers and so on and so forth, and also connectivity for also other, like the animals in your house and so on and so forth. So here the enablers for such for the smart home are the easiness and time saving of the deployment of such a network. This also, we have a social and sociological aspect, which is related to the status and the social engagement that we take, and also the privacy and security that we want to ensure for such connectivity. Now, if we go at the smart mobility inside the smart city, so here you will have, again, other type of connectivities, which are longer range, which are higher data rate, and which interconnect also to the land infrastructure, like the base stations, but they can interconnect also to the satellite connections that we have, and also, for example, to the localization solutions like GNSS and so on. And also they interconnect not only the fixed network inside city, but also the moving, let's say, entities that can be either individuals, so pedestrians, or individuals inside their cars, or the connectivity of the cars, and so on and so forth. So there are other aspects to be treated here. So here the enablers of this IoT network at a larger scale are the safety, the security, and the scalability. So this is really the quality of service that is required on such networks is much stronger than the one inside the houses. And last, so this is the example of the industrial connectivity, so the smart industry. And so this is including also production, plants, units. It includes also transportation of goods. It includes also what we call the medical environment, so the hospitals, but it includes also the transportation infrastructure on the land, like the trains and so on and so forth. So other type of connectivities. And here the enablers are the reliability of such networks, the security, of course, and last but not least, the return on investment. So this means that these are really very heavy investments, so they have to be thought correctly so that they bring back to in return very quickly. So these are, let's say, the 3 examples of such types of IoT network and networks. So embedded one in others, and what are the type of connectivities that they need. Now I would like to explain you. So in the frame of the strategy of ST that I'm presenting you. So okay, so we need such connectivity. So we need to provide solutions for this connectivity, but we need to provide other type of things that are included in the IoT nodes. And here I'm talking about sensors. So ST is also producing a lot of type of sensors. So here is an example on the imaging sensors that we produce here. And more precisely, these are ranging precision sensors. This is called technology called flight sense. So these are distance sensors where you emit a pulsed infrared light, so photons. They hit the target, they come back in a sensor, and you count the flight time, and you deduce with very, very big accuracy the position. So these are type of sensors that we will be using in a lot of IoT devices. Another example of sensors are the inertial, the mechanical sensors, what we called MEMS sensors. So we also have a very wide variety of such sensors that are summed up here. So like accelerometers, gyroscopes, magnetometers, and then a co-integration of several types of these sensors into modules that are a certain number of axis inertial modules, 6 axis, 9 axis. Also, we can have what we call an e-compass, and also solutions for optical image stabilization. And then depending to the IoT market segment that we are targeting, we can qualify them either in, let's say, high accuracy solutions, like for gaming and very precise gesture detection. They can be very low noise solutions, like, for example, the optical stabilization inside the phone. They can be always on devices, so very low power consumption, like, for example, in all the wearable devices, like for, in your connected watches, you have many of them, or also for other new markets, like for gaming and, I don't know, drones and things like that. So we have also this very wide range of solutions in order to enable the IoT devices with the needed sensors. And then, as I said, so these IoT nodes, they need to have some intelligence together with them. And this intelligence comes into a small processing unit that is called a microcontroller. So in ST, we have a big family of microcontrollers called STM32, where we have a very wide portfolio of solutions that permit to address smart applications with more flexibility, energy efficiency, and power and processing power. And then around these STM32 microcontroller units, we have all these kind of connectivities that we already talked about, and we have also integrated together with them adapted the needed security level in order to have this secure type of communication. Regarding this STM32 portfolio of products, so we have really many subfamilies depending on the computing power that is requesting and on the consumed energy that is allowed. And we have ultra low power family, a mainstream, and what we call a high performance. So ST Microelectronics is worldwide leader on the market of the 32-bit microcontrollers, this excluding automotive market, and so that the number of units produced and shipped is really vertiginous, and we are leading the markets on wearable, automation, and healthcare. Now, in terms of security, that comes together with inside these IoT nodes coming together with these microcontrollers. So we have different layers of security coming from basic one up to very high one. So for the basic security, this is what you would have in your wearable devices. And then you will have a much higher level for all what is inside the smart home, and also a part of the healthcare and home appliances. And then you will have the highest security implemented in all what is related to payment units and to personal identification. And these solutions are implemented seamlessly inside our microcontroller SoCs with hardware and or software solutions. And this really really enables us with the exact needed security level with respect to what we want to do with our IoT nodes. Okay, so after having seen these different kind of application for IoTs, I come back to my slides. So as I said, so these smart whatever, so they have in common, so the things on these 5 pillars. And now, as I said, all this is integrated in a system on a chip. So you need a technology for that system on a chip. So it happens that we have at ST Microelectronics, we have also developed the CMOS technology that is enabling this integration path. And this CMOS technology is called FDSOI, like fully depleted silicon on insulator technology. And now, so let's go to another part of my presentation related to this FDSOI technology, which is by construction energy aware, and it's the most suited technology for such energy efficient microcontroller solutions. So this technology, let's say, is the best choice of integration. So for IoT solutions, but also for consumer multimedia, also for automotive solutions and networking infrastructure. So it is it is a planar CMOS technology. So planar means that the transistor here lays in parallel with the mechanical bulk, with the mechanical substrate of the silicon die. So the specificities of this transistor is that it lays atop of an ultra thin buried oxide layer, and the transistor is drawn atop it, and it sees itself dielectrically isolated with respect to the bottom of the structure, which is called the body of the transistor. This gives a total dielectric isolation to this transistor. This enables also no need for channel doping for the good conduction inside the transistor channel, and no need for pocket implants on the sides of the source and drain in order to enable a good analog performance of these transistors. And it comes out that thanks to these features, this is a very power and energy efficient technology with very good analog performance and very robust to mission critical applications as well. Well, this is a part that I will not cover today in my presentation. So as well, so as said, so the transistor lays atop this buried oxide, but we can have access here from the side to the volume underneath this transistor. So this is doable because all these dimensions are very small. So in the 28 nanometer FDSOI technology node from STMicroelectronics, this buried oxide is 25 nanometers thick, and the film also here on the conduction channel is 7 nanometers. So this means that this volume underneath the transistor, so it's electrostatically isolated from the front side, but it's not so far from the front side. So this means that if we apply a voltage on the volume here underneath the buried oxide, this will induce by electrostatics a change in the threshold voltage, in the VT of the transistor on the front side. And this is called body effect. And this body effect, it comes out to be a very powerful tool in order to bring flexible transistors that have a variable threshold voltage done through this tuning knob. And this is really a very big enabler for performance boost, for a reduced power consumption at a given performance, for process compensation, reduction of the margins to be taken, and it is also seamlessly included into the EDA design flow. And I would like to give you a detailed example of how these transistors are made and how come that we can do this through this body biasing. We can do a threshold voltage variation. So here I am showing you a cross-section of a regular bulk type CMOS transistor. So this is an NMOS cross-section, this is a PMOS cross-section, and you can see we have here open the accesses for the body of the transistors. And here you can see that if you apply a voltage here, you can do a bit of a body effect, so modulate what's happening here in the conduction channel of the transistor. Nevertheless, this voltage to be applied here is very limited because after a certain while, which comes very quickly, you will open this parasitic diode's body to source respectively drain. So this is in bulk. Now in FDSOI, if you look here on the bottom left, so you have these transistors atop the buried oxide. So it's an NMOS, it's a PMOS. And here you have the body connection here on the side. And here what you can see is that the source and drain topologies, they are insulated from the body by this buried oxide. So this means that we can apply a voltage here on the body of the transistor, and it will not impact, it will not open anything toward parasitic towards source and drain, and it will be only limited by this big diode P well, for example here to deep N well, which is like a Zener diode opening after 3 volts in modulus for sure, for one or the other side. And this means that on these transistors that we call also regular VT transistors, we can apply here a very wide range of voltage, and as a result, so here we call it reverse body biasing, as a result, the threshold voltage of the front side transistor will vary really with a very big amount. So from, let's say, from 0.4 to 0.6 volt and so on. So that's really very significant. Alternatively, for analog design and low power, we have the low VT transistors, which are called also flip well transistors. And here we can do the same thing. It's called forward body biasing, and we can again change the threshold voltage with a very wide amount. So this makes, so this and all the other features make that this technology is very simple for analog integration. We have very good performance in analog, in noise. The short devices are very efficient. We have this new tuning knob with the threshold voltage. And as we are at the 28 nanometer technology node, we can have a very high FT and F max. So this means we have a lot of margin if we design in the IoT space, which is at lower gigahertz frequencies. And here there are some examples of behavior, of intrinsic behavior of the transistors compared in FDSOI with respect to the same node in terms of gain of density of GM that we get per unit of current and also of noise. And again, the story with the body biasing, so we can apply a very big body biasing voltage range here, and we will get a significant variation of the threshold voltage of more than 200 millivolts here, for example, for a control body bias voltage of more than 2 volts. And this is really much, much bigger than what we could get in bulk technology, where you can have very few tens of millivolts, like is shown here. This is also, I will not spend too much time, so this is also the behavior in frequency with the measured FT and F max, which are very high, so above 300 gigahertz. And also this is the example of the switches performances. So, you know, for data converters, you need switches like CMOS switches that you control on and off, and you want them to behave like a 0 ohm resistance when they are on, and with like a big, like an insulation when they are off. And unfortunately, in real time, in real life, in real regular CMOS, so you will have a switch on resistance, which shows like this, and which can vary a lot with respect to the voltage across the terminals. This is in regular CMOS, while in FDSOI and applying body biasing, this permits a very big linearization of these CMOS switches, and this makes their on resistance almost flat and very low. So this means that this technology is very advantageous for very good data converters. Now, in the last part of my presentation, I want to show you a concrete example of an IoT solution that is, we see it like an IoT of the future. So this is an example of collaboration work that I have been doing with the IMN lab in Lille and with the BWRC lab at UC Berkeley in California. So it's called the Human Intranet. So the idea here is to build a network of sensors and actuators around the human body. So each human will have its own network. So this network, so it is connecting what? The signals coming out from sensors and actuators. So sensors, you can have motion sensors, you can have chemical sensors, you can have gyro sensors, or you can have sensors and actuators, for example, for a prosthetic arm. They need to be interconnected among them. So we need to define a network that is connecting them in such a way that this minimizes the energy consumption, and they need to be enabled with computing power, a bit of computing power that is low cost. So in terms of interconnecting them, so we have proposed, so what we wanted for this solution is to optimize it in terms of energy efficient at all the layers, meaning at the definition of the network, how to define the network in order to be the best energy efficient, how to define the MAC layer, which is controlling the operation of this network, and then how you implement the hardware that is interconnecting these nodes in order to be the best energy efficient. So in terms of network, we have proposed a solution which is a mesh of stars, meaning that we have big nodes here that we call hubs that are in a mesh interconnection, like you see here. And each hub has many stars interconnected in many leaves, so here, that are connected in a star connection to it. So for example, you can think on a prosthetic arm, you have a hub here and you have small leaves on all your fingers that are connected to that hub. And now what kind of signals we want to connect? So we want to sense or to actuate signals with low data rates, like temperature, chemicals, biometrical impedance, oximeter, ECG, or signals with higher data rates, like, for example, for motion or neural recording. So this means that the nodes, the silicon hardware that we put inside the nodes or the hubs or the leaves have to be able to serve a flexible range of data rate in terms of what we want to transmit. So this was one optimization. The other optimization that we did is in terms of how this network behaves. And you know so you have studied in school frequency synthesis units. So I know people that studied at ENSERM. You have had classes of Professor Jan Deval related to frequency synthesis like PLS. So first of all, they are quite complex systems, but also in a communication system, what consumes the most is the frequency synthesis unit, and it has to be stabilized. So we wanted inside this solution to optimize it in terms of this frequency, let's say, cadences in that. So we did it in a opportunistic way, and we said that as it is a network which is connected to the human body, it can use opportunistically something that exists in the human body, and it is a clock, and that clock is the heart. And as long as your heart is beating, so you will have a integrated, so you will use this heartbeat in order to have the synchronization for your network. And when your heart doesn't beat anymore, so you don't need that network neither. So we have compared this kind of solution. So we didn't do it by hands. We did some scientific calculations, and it came out that this is 25% more energy efficient than solutions that use wake-up radio. So you have nodes that sleep, and you give them a wake-up signal saying, "Hey, I will be talking to you, wake up." And this is much more efficient. The second optimization that we did was in terms of which type of communication we will be using. So the most straightforward that we would have had was the Bluetooth low energy standard to use. The story is that the Bluetooth low energy, so it works at 2.4 gigahertz. You need antennas, which are quite, let's say, the smallest ones are like this, and you cannot put all this on your human body, and then they are sending out, so the beaming of this network is not really connected to your body, so they can be around your body and somebody can come and hack your system. So we studied other type of communications, and we came out that the best in terms of energy efficiency and of security of data is the capacitive body coupled communication. So this means that, so this is not, let's say, anymore theoretically speaking, wireless communication. It is communication through the skin, through your skin, through the upper layer of your skin, which is like 70% water. And you send electrical signals very weak, okay? So nobody has been harmed through these experiments. So there is standardization, there is FCC standardization covering this. And so the signals are sent through the skin, through the body, the skin of the person, and it is again opportunistic as it is a network on a human. And this permitted also to optimize. So now to go further on, so this kind of communications on capacitive body coupled, they can work at any type of kilohertz to megahertz and some gigahertz frequencies, but there are some optimal frequencies. And we have determined these optimal frequencies. So these were around 450 megahertz with a bandwidth of something like 150 megahertz. And we have used ultra-wideband pulsed signals, which are, you know, in the nature, the most energy efficient signals that can exist. Here I show you the example of silicon-based implementation of such a transmitter for this kind of system, where we are using a novel architecture of such a transmitter. So we use local time base that can be synchronized from the heart, which is based on an unlocked ring oscillator. This ring oscillator will be controlled by body biasing in order to get some specific features. Outside of these ring oscillators, we get 5 operation phases, as you can see here. And through these 5 phases of the same signal, by doing an edge combining, we will generate a frequency multiplication, and then we will apply on it a Gaussian pulse shaper that will permit us to build up this system, this wave, which will then be amplified through a switch capped power amplification solution and then transmitted. And thanks to this solution, we were able to propose. So then, okay, and then sorry. So then there is the modulated data that is input here and transmitted. And thanks to this solution, we were able to be the most energy efficient solution presented here. So this is the red curve is our solution, but also which is flexible in terms of data rate. And okay, so this I have commented, maybe I will skip. So in terms of this ring oscillator, and these are things that you might be working on like these days, we are using this ring oscillator. So it's an odd number of inverters that are one after the other. So they are interconnected in a pseudo differential topology with this kind of latch structure, which permits to lower the phase noise, and their operation is also controlled by the body biases of these N respectively P transistors inside the inverters. And then I said that so we use these five edges of the signal and the pulse shaper in order to here. So pulse shaper edge combiner permits us to generate a signal with this and an ultra wideband envelope that we are then amplifying by switch cap power amplifiers. And this was enabled with the feature of the body biasing that permits also to control the shape of this emitted signal and also to calibrate the frequency generation. So this brings me to the conclusion and some takeaways of this presentation. So I have shown you an IoT solution of the future that we call the human intranet. So this would permit us, for example, to do neural recording and stimulation. This would permit us to have seamless prosthetic arm integration with the human body. This can enable also the continuous glucose monitoring and towards the insulin pump, for the artificial pancreas. This will permit seamless integration of all kind of motion sensors on our body, of this kind of monitoring things that we would have, or like, for example, intelligent hearing aids that permit us to know where that sound comes from, and so on and so forth. And these both for healthy people and for disabled people. So my subtitle of this presentation was "Our Designs Will Change the World." So a human enabled with all the features will be another human. So let's say will be enabled person, and this will happen thanks to the designs that you and I, so mostly you, because I have done a big part of my career, will propose in the companies or in the structures that you will be working in. And I want to bring you a bit back in time. So you are a lot of young people here, and I would like that you don't smile too much. So the the communication devices that existed when I was your age, and when I was finishing my electrical engineering studies and doing my PhDs, are kind of presented here. So this was a gaming console. This was a mobile satellite phone. This was a device that was called a pager. So that was very before having these mobile phones, we had these pagers that was called tam-tam, and that you could receive very short messages, and that helped you not to forget the bread when you were going back home in the evening. Okay, then we had something that was really revolutionary, and it was the precursor of World Wide Web, which was the Minitel, that we could interconnect us to a network of information from our homes. This was the device, the iPod, where we could store some 20 mega of data of music. So that was wow. And this is how looked the TV sets when I was 20 and so. Okay, so this was only, let's say, 25, 30 years ago. And today we are here. So this is how look our connected device. This is how look our communication device. They really have a lot of shapes, a lot of formats. They serve a lot of things. And this is only the beginning of what we can do with it. And I would like to end up with the vision that we carry on inside my company. So our motto is life.augmented, meaning everywhere microelectronics make a positive contribution to people's life, we are present. And I hope that you will find some good ideas from here. And I would like to thank you for your attention. This is a picture of the very beautiful site where I work. I am exactly in a building by here now, okay? And thank you for your attention, and I'm willing to take some questions, and I was a bit late. I'm very sorry.
Thank you very much, Dr. Andreia Cathelin, for this very interesting talk. So does the audience have some questions? Okay, so I have one question. So with Moore's law, we're going down and down in technological node, but I think we are reaching a bottleneck on the size of the transistor. So so what would be the next step for FDSOI? Will it go down in scaling? Are your thoughts on this?
So the technology scaling, yeah. So what you are asking, the more scaling. So it depends what you need to do. So if you need to do very high, very intense computing, so yes, you need to go on very low scale. I mean, very scaled technology nodes, and this is the more trend that exists today, and I I heard some announcements for 1 nanometer technology nodes, okay, but this is not the trend on which we have FDSOI technology. FDSOI is now considered a more than Moore technology node. This means that this is a specialized technology that is serving the energy efficient market segment. And for example, for doing IoTs, you will not need very low lithography nodes, because they will be costing a lot and they will be consuming a lot. So in terms of how fine you can scale the FDSOI technology, yes, so we have announced to start working on 10 nanometer technology nodes. So this is a bit of the let's say semiconductor physics limit on such technology. But then if we will be needing to scale more, but I tell you, this is more, so it's not exactly what we are looking for. There are other technology solutions that permit to go there.
Okay. Thank you very much for this answer. Do we have a question? Yes, Roman. Ouais, peut-être bien ici. Ça te dérange pas.
I have many, but just to start, knowledge about the question around the IP that can go under the skin. What is the characterization around the temperature? Because for me, in STM32, we characterize from minus 40 degree to 125, but for this kind of application, I think it changed.
Yeah. You will not need to bring it up to 125, or you will do it only once and then your human will be baked. Okay. So here the temperature range is much smaller, and it will be between, let's say, 35 to 40. So it is much smaller. Or you want to do it for other type of application. But yes, so the temperature range is very small, and the temperature of the operation of such network will be the body temperature, because it's really connected on the body. So yes, maybe you can go, how to say, you can go a bit lower in temperature, a bit higher, but not so much, because the human body stops working properly at 30 degrees Celsius, for example. Even if you are in a very cold ambience outside, if you don't dress, you die. So it's these are the physiological limitations of the body will be the operating range of such a product.
And from your point of view, in terms of design, is it hard to respect this kind of temperature range for this kind of IP? Because it has to be low power consumption and so on. And
no, this is an enabler for the solution, because as said, so we don't want to use locked solutions in terms of frequency synthesis, for example. So this means that we need to lock it periodically for, like, with body biasing control and so on. So it is opportunistic. So the solution is opportunistic because the frequency range is not so big.
Okay, and just to finish, I've heard something about this kind of IP used in body under the skin for, I think it was in Sweden or in Denmark, I don't remember, but they use that for employees going in their firm to go there. And how do you think that can be welcomed by the public about this kind of application, by being under the skin, it's invasive and so on? So how the market is?
No, there is no market. So that is something. So yes. So all these kind of IoT devices around the human body, they have to be controlled by very strict ethics norms, okay, and solutions. So our network is supposed to serve your body. So you, Roman, you have your network that is connected on your body, and you control to
with the connection.
do you hear me now?
Yeah, now, yes.
So so in a first step, so this kind of network, so is for your body, is on your body. Now we can have some sensors. We thought about some sensors that can be inside the body, for example, for brain stimulation and so on. Okay, but we haven't thought of it as a control network, which is controlled from outside the body. Okay.
Okay.
So this is what we thought now for sure. All these kind of solutions, so the ethics around it have to be thought before developing whatever. So yes, so the guys that had a chip under the skin, so that people they can badge with their hand, and then yeah, okay. So that's a bit of a big brother. So yes, so there are ethics, and I mean the legislation. So this is more, let's say that this is also politics. So how the legislations in the countries, they allow it and so on. But yes, so normally you need to have, and that's why, so our solution, we had a big constraint of security, and that's why our solution is really confined in your skin. So you see, like I cannot come a device and put it next to your skin and hack you, because I will not be able.
Thanks.
Thank you very much, Andreia, for these answers and this very nice talk. I think you will see the students here very soon, so maybe they will have some questions for you. And so thanks again for this very interesting talk.
Thank you.